Oh, oops. Okay, started my video off to a good start. Um, Finally, we're into maybe one of the most important chapters. This is a very, very long chapter. It'll take us a couple of weeks for sure. And it covers Unit 3, Chemical Bonding and Nomenclature. Now, nomenclature, guys, is just a fancy word for naming. So by the end of this chapter, or unit, you will learn how chemical bonds are formed. We're going to look at things like states of matter. And then most importantly, by the end of this chapter, you will learn how to name ionic and covalent molecules, acids, bases, ionic compounds, molecular compounds. Pretty cool. So just hold on, my dog is going crazy, and I'll be right back with the introduction. All right, so sorry about that. Back to Unit 3 here. The first section we're going to do does relate to your lab this week. And again, you didn't need this to do that lab. It was a pretty straightforward experiment. And if any of you haven't done the lab this week, I know some of you have it at 3:30, you'll kind of see what I'm talking about today in the lab. We're going to look at solids, liquids, gases, phase changes, boiling point, and then I won't get to this today, but tomorrow's class, we will cover kinetic molecular theory. So important, such an important topic for future chemistry courses or even this course. So today I'll probably just do the first part of section 3.1. All right, I just have a message in the chat there and then I'll get started. I wish the dog could teach you guys today. If she'd probably do a pretty good job. But anyways, I think she's good now. I got her a little snack, so she'll be busy eating that for a bit. Okay, 3 states of matter. This is, very basic science. You've probably heard of these states since you were kids or teenagers at least: solid, liquid, gas. The easiest way to think about these 3 phases is to just think about water. Solid water we call ice. You guys obviously know what ice is. You put it in drinks, like you go to the movies, you get ice in your drink. That ice will melt and turn into a liquid. So liquid water is the most common form of water. You can see it right here. And then if you heat up water, add enough energy, it can turn into a gas. And that would be like steam, very warm, very hot. So solid, liquid, gas, as we increase energy or heat, we can change phases. So you can melt a solid into a liquid and then boil or evaporate a liquid into a gas. So we're going to look at the 3 states. I'm going to give you some information on each of them. These are good for multiple choice questions, wink, wink, wink. So you'll, you'll definitely need to know some of this for tests or final exams. So solids. I have on each slide, guys, I have the same picture with the different phases, and I really want you to kind of look at the picture and look at the difference between the little purple balls. These are particles or molecules. Solids are tightly packed particles, very tightly packed. So think about if you're sitting at a desk right now or your kitchen table, you have a laptop and a keyboard in front of you, maybe a pen and pencil. Those are solids. You can't put your hand through them. And think of the 3 phases. Think of, trying to put your hand through the desk. It stops, right? I'm pushing on my desk right now. There's nothing happening. Then think about going swimming. You jump into the ocean or a swimming pool. You can push your hands through the liquid water. Now think about the room you're in. The room you're in is full of gas. It's full of nitrogen and oxygen and carbon dioxide and other gases. And you can easily wave your hand and walk through that gas. So when you're thinking about particles, solids are so tightly packed that you cannot pass through them. Okay, you can break a solid, you can, cut a table in half, but you can't put your hand through it like water, which is a liquid, or gas. So solids are tightly packed. This is the big one, and each of these states of matter have a different kind of version of this phrase at the bottom here. Solids are the state of matter that have a constant volume and a constant shape. So look at this solid in this beaker here. This solid is a solid. It does not take the shape of the beaker. Okay, this is a beaker or a glass. Because this is chemistry, I'll call it a beaker. If you take a couple Lego blocks or a pen or a pencil or even an ice cube and you put it in a beaker, it doesn't actually take the shape of the beaker. It keeps its shape. The only way to change the shape of a solid is for you to physically do so, meaning you could crack your pencil in half, you could melt the ice. But again, that's changing its phase. So solids have a constant shape. They also have a constant volume. So if this was a cube, the volume would be length times width times height, and it's constant. The volume of that cube does not change. Okay. Now, this next phrase might be a little confusing if you've never heard the word compressible. Compressible means squish or squeeze. So basically, when you compress something, you are trying to lower the volume, meaning you're trying to reduce the volume. You know, you're squishing it. So if I had a piston, this is called a piston. It's a disc that takes the shape of the beaker, like it, meaning I mean it fills the beaker, and I want to push this down. It will not compress the solid. The only thing that might happen if I push down or try to compress this solid is it will break. It will not compress, meaning the space between the molecules will not get smaller. The volume will not get smaller. It would probably just crack or break. Okay, so again, think about it. You're trying to squeeze your pencil or squeeze your, if you have a computer mouse in front of you, it's not going to compress like a balloon. It would probably just crack. In terms of the speed of these particles, remember, kinetic energy is the speed or motion of the particles. Solids stay in the same place. They have the lowest kinetic energy. This I'm going to come back to later. Okay, I'm not going to talk about it today because we're not ready for this. But in section 3.6, towards the end of this chapter, we're going to look at something called the intermolecular forces. These are the forces between the molecules in a compound or in a sample, and we're not ready for that yet, so I'll come back to that later. The last thing I'll mention is that solids have the highest density of all the phases. Because the particles are so close together, their mass related to their volume is very high. I know this is not the best example, but some of you who did lab 3, and I know lab 3 is a touchy subject because not everybody got to do it, but in lab 3 we measured the density of a liquid and a solid, and the solid was much higher, like 8 to 10 times more. But you don't need to do the lab to know that. Solids like iron, metal, steel, gold, they're much more dense than something like water or oxygen gas. And Aman mentioned in the chat there that she knows kinetic energy from physics, and that's exactly right. A lot of your first year courses, specifically chemistry and physics, have a lot in common. Things like significant figures and states of matter, kinetic energy. That's the cool thing about science, and especially chemistry and physics. They're kind of good friends. They're very much related. They all share a common theme in that they're all basically based in mathematics, but chemistry is a little less math than physics. Okay, so on to the next state. And guys, you'll notice that these slides have a similar layout, meaning I'm talking about the same thing for each phase. So liquids, their particles are not fixed in place, meaning they flow. If you know the word flow, like think of water moving in a river or the waves on the beach, right? The liquid water moves. And because of that, water, or I keep saying water because it's the easiest example, but liquids do not have a constant shape. When you freeze something and it turns into a solid, it takes a shape, and that shape stays the same unless you physically do something, meaning you break it. But liquids are cool. They don't have a constant shape. They will take the shape of any container you put them in. So think about when you go to your refrigerator and you pick up a bottle and think in your head, think of the shape of the bottle of, say, milk or juice or Pepsi or Coke or whatever. The liquid is filling every nook, every cranny. I don't know if you know those words, every gap in that bottle, the liquid will fill. Solids don't do that. And when you pour that liquid out, you take your bottle of milk or bottle of water and you pour it into a glass or a beaker, the liquid will then take the shape of that container. Solids do not do that. And I know you might be thinking, well, if I pour sugar or salt, it takes the shape of the container. That's only because the salt or sugar has been squished or mushed into little tiny crystals. But there are still gaps in between those crystals. They don't actually completely fill that container that you're pouring it in. And again, an easier way to think about the difference is something bigger than sugar. So something like a Lego block or marbles or dice or something big. If you pour them into the container, a solid, it will always have gaps between the solids. They keep their shape. Marbles or tennis balls, they're still going to be a ball or a cube. Uh, but liquids, they flow and they'll take the shape of the container. Now, liquids also, though, like solids, do still have a constant volume. They are a little more compressible, but not as compressible as gases. Gases you can compress like crazy. So again, if I have this piston example, if you tried to push this shape down on like water or milk or coffee or any liquid, it won't really compress. It won't move. And you guys can try this at home. I'm sorry, I'm just reading the chat there. You can try this at home today if you have a water bottle or some sort of container, not glass or anything, but like plastic or something. You can do this at home. Take a water bottle, completely fill that water bottle. I mean, completely fill it to the very top. Okay, so there's no air or anything in that bottle except water. Put the top on the bottle and then squeeze. And you'll notice that the water really doesn't compress. Like the bottle doesn't squish or shrink or reduce its volume. The liquid pushes back so much that you can't really compress it. Gases, I'll show you on the next slide, are much different. So liquids are slightly more compressible than solids, but still they aren't very compressible at all, which means they have a constant volume, which Iman mentioned in the chat, like that they have the same amount, or technically they occupy the same space. And I can give you one more example for this. If you're into cooking or you go into your kitchen, you probably have measuring cups in your kitchen. Okay, quarter cup, half cup, 1 cup. Roughly 250 milliliters is a cup. The volume of that liquid does not change. You can pour it into another container, you can pour it back into the cup. It's always going to be a cup. And again, a cup is roughly 250 milliliters. I think the US cups are different. Let me just see. US cup 2 milliliter. 236 milliliters are in an American or US cup, which is, again, if you've never baked in your life, you might not know what I'm talking about. But if you have baked or you've cooked, often the recipe will say add a quarter cup or add 1 cup of chicken stock. That's a measurement. And that liquid doesn't change. A cup is a cup. All right. Um, Liquids do move more than solids, and the higher kinetic energy allows them to flow or not be fixed into place. So you can pour a liquid, you can move a liquid around between your fingertips. Think about sitting in a bathtub or a swimming pool. You can move those particles around nice and easy. They literally flow. This we'll talk about later, of course. So again, I'll come back to this concept, but they're intermolecular forces. The forces between the molecules in a liquid are a little weaker than a solid. They're not as attracted to each other. The word I'm getting, the question I'm getting is, what does the word intermolecular mean? I will come back to this in section 3.6, but the word, you can break it down. Inter means like kind of between things. Okay, so think of the internet. The internet is when your different computers all over the world are connected in a network, internet. So inter means like the relationships or connections between something. Molecular means molecules. So intermolecular forces are the forces or relationships between molecules in a sample. Okay, and we'll talk a lot more about that in section 3.6, but intermolecular, the forces between molecules. Internet, the connections between computers. Intermolecular, the connections between molecules. Okay, and again, it's kind of the relation between atoms, but more specifically, the relation between like molecules. So it's actually a really cool topic. Intermolecular forces tell us why something like water boils at 100 degrees Celsius, but something like ethanol or methanol boil, or propane even, boil at much lower temperatures. They're the forces or the attractions between molecules. And we will talk about that later. I promise. I'll get into that a bit later. So if you measure the density of a liquid, it's typically lower than the solid. There's also, I won't get into it, but there's exceptions to that, but that's another topic. If any of you students are in occupational health and safety or environmental health and safety, you might do a course with me later called environmental chemistry, and we'll talk about the density of things like water and how cool it is, but that's for another course. Okay, gases. Oops, sorry. Gases have a lot of space between particles, and you guys can test that right now. Take your hand, wave it in the air. You should feel basically nothing. Okay, when I wave my hand above my head, and I'm doing it literally right now, I don't feel anything. I might feel a little cold from the air conditioner, but I don't feel anything, because gases, their particles are crazy spread apart. Like, they have large gaps between them. They're very fast moving. They have the highest kinetic energy. And because they have a high kinetic energy, it means, that's why they're boiling. And it's really weird to think about this. When you think about boiling water, you think about heat or danger. Like, I know when I pour a cup of tea or coffee, it is so hot because it's boiling. I can't even touch it. But honestly, guys, in the room right now, in your room, wherever you are, in a classroom or in your house, you're sitting in boiling gases. The oxygen, the nitrogen, the carbon dioxide that's around you right now is technically boiling. They have incredibly high kinetic energy, and they're moving at very high speeds. But unlike water, boiling nitrogen, boiling oxygen are such low temperatures, it obviously doesn't hurt you. So it's kind of interesting, but you guys are sitting right now in a room full of boiling gas, but it doesn't hurt. Gases, they do not have a constant volume. And this is because, unlike solids and liquids, you can compress a gas. And I mean, the easiest example here is think of a balloon. Take a balloon, blow it up fill it with air and you can squish that balloon. You can't do that with solids or liquids. You can't really squish them or lower the volume. A balloon might not be the best example, but you could take that water bottle example I mentioned before. Fill a water bottle with water, completely fill it, no air inside, put the cap on, try and squeeze it, nothing will happen. Dump all the water out of that water bottle so it's filled with air or gas, put the top back on, you will be able to squeeze that bottle. You will be able to compress the gases in that bottle. And because of that, gases do not have a constant volume. They also do not have a shape. A gas will take the shape of the container that it's in. Okay, pretty straightforward concept. That's why, like, when you're sitting in a classroom and somebody's wearing a lot of cologne or perfume, the gas from the cologne or perfume is going into the air and it will eventually take the shape of the room. It will fill the entire room. So I notice sometimes when I'm in the classroom, a student will walk in and then 5 minutes later I can smell some cologne or perfume. And that's just because the gas is filling the room. So eventually the perfume or cologne smell will be in the back, in the front, and every corner of the room. Pretty cool. Again, we'll talk about this later. They have the weakest intermolecular forces, and that's why they're so spread apart and they're moving around each other very quickly, and they're very, very low in density. The mass of the air in your room, for example, is very, very low. So again, think about your room. The air has very little mass, but the volume of the room you're in, if you're in your bedroom or kitchen or classroom, the volume is huge, so very low density. If anybody missed lab 3, density, by the way, I should have mentioned this, is the mass of an object divided by the volume that it takes up. So the mass of a gas divided by the gigantic volume of the room you're in is very low. Okay, I have to end pretty shortly because I have to get ready for the lab, but I'll do a couple more slides. I'll talk about phase change. I might talk a little bit about vapor pressure, we'll see, and then that's it for today. All right, so just give me maybe 5 more minutes or so, and that'll be it for today. Okay, so you guys are expected to know at least 5 of the 6 phase changes. And I say 5 of the 6 because we typically don't talk a lot about deposition in chemistry 1120. And I'm not saying you shouldn't know it. I just mean if there are phases or phase changes to know, it's melting, freezing, condensation, vaporization, and sublimation. Now, some of you, if you're like me, I never heard of sublimation until I came to, a university or started doing chemistry. Melting and freezing I knew since I was a kid, right? Especially in Canada where there's snow and ice all the time. Well, solid would melt to become a liquid. A liquid would freeze to become a solid. They're very common phase changes. The next 2 over on the right of the page, a little less common, but very important. When you heat a liquid so it turns into a gas, we call that vaporization. And you might have heard the term before in science, evaporation. Evaporation is the phase change where a liquid turns into a gas. Condensation, you guys see condensation every day, or well, maybe not every day, but every time you take a shower, you will see condensation, especially this time of year on your window or on your car windshield, you will also see condensation. When you're out or you're getting into your car or looking out a window, if you've ever noticed liquid water on your windshield or on, like I can look out in the nights, I can look out my window and see liquid water on the window, that is condensation. What's happening for condensation to happen is in the air outside in Doha right now, it's 50 degrees Celsius sometimes in the summer. Today it's not as hot, it's only 37 today according to my phone. But in the air, outside is water vapor or gas, water as a gas. So when you guys, if you ever hear the word humidity and someone says, oh, it's so humid today, that's because there is a lot of water vapor or water gas in the air. Now, when that water vapor or gas in the air touches something cold, like your car with the air conditioning running, or your apartment or villa window, when it touches something cold, it lowers the temperature, the energy gets lower, and it turns into a liquid. And that's called condensation. So every time you shower and you have a warm bath or shower and you get out of the shower, you might notice that your mirror in your bathroom is covered with steam or water. That's because the hot steam from your shower creates water gas. The gas touches your cold mirror, turns into a liquid. That's condensation. So guys, you need to know what melting is, freezing, condensation, and vaporization. You definitely need to know those 4 phases. The other one that I would say might be worth memorizing is sublimation. This one's really cool. This is when a solid turns into a gas and completely skips the liquid phase. Okay, it's pretty rare. I don't see this very much, but one place that I do see this in nature, well, no, I guess I shouldn't say nature, but in real life, is if you go to like a fancy restaurant, sometimes they'll send you like a drink, or you see it sometimes at coffee shops too, like this nitro brewed coffee they have at Starbucks. They use different chemicals to make things really cold. I think the nitro coffee at Starbucks is a cold brew. I don't know much about that, but I know in some places I've seen things served with dry ice. Dry ice is frozen or solid carbon dioxide. And when you take solid carbon dioxide, and you can Google this today if you want, there's definitely some good YouTube videos out there. When you take dry ice or carbon dioxide in solid state and put it in a liquid or have it at room temperature, it immediately boils or turns into a gas. And I have a little video on the next slide. This is not dry ice. I got this from another instructor. Oh, this is weird. It worked in my last class. Hold on now. See if I can get this to work. It says it cannot play the media. That's no good. It literally worked in my last class. Just hold on. Let me exit my PowerPoint and try this again. Okay. Oh man. I'm just going to stop screen sharing. This will be the end of today, guys, because I do have to go to your lab. So I'm going to exit my PowerPoint, or try to. The computer's giving me a hard time here. Okay, sorry, I'm gonna try to open my PowerPoint again and see if that video will play. It literally just worked in my last class, so maybe because I left my PowerPoint open, it stopped. So just give me 1 second here. All right, I'll share my screen again. And this is the end of today, guys, because I have to go.
Okay, Mr. Have a nice day.
Oh, no, I'm not going yet. Well, you can go, but I'm not going yet, man.
Yeah. So we leave.
No, don't leave. But you can. I mean, if you want to leave, you can leave. But I'm not done.
No. I'm asking if the class if it's done or not.
It's not done.
Not yet, huh? Okay.
Nope. I'm having crazy problems here. So hold on. Something's going on here. Okay, maybe it is done. My PowerPoint is like not working here today, and I can't even get the Zoom chat open. So I think maybe tomorrow, guys, I'll show you that video. My PowerPoint is just not cooperating with me, or my Zoom especially. So I will end it there today. You guys can go, and I'll see you tomorrow. I might actually have this working now. Let's see. All right. I don't know if this will work. No. Can you guys see that? Can you see the sublimation happening in that video?
Yeah, Mr. Peter.
Yeah, I'm sorry about that. And now this is going to be on YouTube.
No problem.
My computer just decided to like say, nope, I'm not going to work for you today. But I did manage to get it working. Something's going on. But there it is. That solid chemical there is immediately boiling and turning into a gas. That is called sublimation. So guys, I'll leave it there today, and we will continue this tomorrow. Have a great day, everybody. Yeah, that's it. So I'll hit stop record and we're good to go.